I'm excited to welcome back to San Antonio, Joe Schornak. He is here with PickNik. He's a senior robotics engineer at PickNik. He did his master's at Worcester Polytechnic in the Boston metro area, undergrad at Rose-Hulman. He's been focusing a lot on perception-driven robotics at PickNik, in particular in unstructured environments and working with objects that haven't been seen before. Joe, I think everything is ready to go. Thanks.
All right, there we go. All right, how's that sound? Good. All right. All right. Yeah, anyway, like Matt was saying, I used to work at Swery, and I remember actually back at the end of my internship, which was back in, 2015 and 2016, I was actually presenting from this very room, so it's sort of fun to be back here. It wasn't the same screen, though. This is a much cooler screen than we had back then, so I want to say. Anyway, yeah, I'm Joe Schornak. I work at PickNik. I'm a senior robotics engineer. Most of the work I do is basically making robots see things and then interact with them. A little bit of background about PickNik. We're located in Boulder, Colorado. We've got a lot of really bright people, a lot of kind of combined robotics experience. We're also a globally distributed team. I live in Boston, for example. So if you ever see a video from PickNik where the robot is in like a sort of a suspiciously homey looking environment with a nice wood floor, that's my apartment. One of our, this will be sort of like a two-parter kind of presentation. So one of PickNik's main things is that we're the steward for the MoveIt project. So we're sort of the key maintainers for the open source side of MoveIt. So I'm going to be talking about some new things that have gone into MoveIt open source this past year, some new features that are possibly of interest. And then I'm going to talk about MoveIt Pro, which is our product that builds on top of open source MoveIt to add a whole bunch of cool new stuff. I'm also taking advantage of the fact that I have a demo slot booked today. So if you should have a chance to get more of a hands-on, close-in look at MoveIt Pro a little bit later. We have a robot set up running a manipulation demo, so that'll be really cool to see. Yeah, so what's new in MoveIt for, I guess this would have been 2023 and 2024. Yes, we released for ROS-I Iron, which is the latest non-LTS release. We try to track the intermediate releases a little bit more closely because people who are adding new features like to use those. There were several important updates to the planning pipeline as far as like how the different steps of planners feed into each other. I'll talk a little bit more about that on a later slide. Stomp is back. My understanding is it went stale, but it's back and you can use this with the planners. There's another slide about that. We have, one thing that's cool. Yeah, we have Python bindings for the MoveIt C++ API. I think there was sort of limited Python support previously, but now there is more of a much closer to one-to-one correspondence between the C++ MoveIt and Python MoveIt. So you can do a lot more things in Python that were previously C++ only. That's really cool. We finished basically a ground-up rewrite of MoveIt Servo, which is the process for streaming Cartesian and joint velocity commands to the robot to make it's kind of like a jogging interface. So there are new smoothing plugins for MoveIt Servo that so you can apply filtering steps to the input commands to sort of tune the output motion as it's sent to the robot as desired. There's integration with NVIDIA's Isaac simulator environments and sort of robotics stack. That's really cool. And then, as always, there were a huge number of bug fixes that went in to keep MoveIt healthy and working well. Yeah, so a few more notes about Stomp. I think this is somewhat familiar if you've been tracking kind of ROS-I robotics for the past few years. Stomp is an optimization-based planner. So given an initial seed, you can apply different costs to the trajectory to sort of drive it in a particular way. So it's common to model like distance to collision or smoothness of the trajectory as a cost. So this lets you influence your joint trajectories in a way that is kind of hard to do if you're just using the sampling-based planners in OMPL. And this synergizes really nicely with the planning pipeline improvements. So two big things to mention here. So we have a new parallel planning feature. So you can actually kind of have multiple planners running alongside of each other. You know, you can have like a really naive joint interpolation planner and then some of the more thorough OMPL planners. And then depending on how you set your termination criteria and your cost criteria, you can say, all right, just finish as soon as you have, you know, a feasible solution. So that way, you know, you can have get an answer really fast if you have a motion that the joint interpolator solves really quickly. Or you can say, you know, keep going for a long time until we're kind of confident that we've kind of sampled the best possible plan given this environment. And then second big thing is that you can chain planners together in the planning pipeline. So this works really well with Stomp. Stomp needs a seed trajectory, and a lot of the time for if you have a kind of complicated planning scene, you know, just the interpolated trajectory from start to finish isn't actually a feasible seed. So now you can use like RRT Connect and have the output from that feed into Stomp, and then let Stomp optimize based on that. So that's really cool. Okay. So the second part of this is sort of a product walkthrough of MoveIt Pro, which is PickNik's product. We frame it as a runtime and developer platform that lets you accelerate implementation of really reliable, complex, unstructured robotics kinds of problems. I say unstructured, a lot of the tools that we provide through MoveIt Pro are meant to be, or kind of targeted towards robots that don't know a lot about their surroundings, or they have to figure out a lot of things on the fly as they're going through the product. You know, since I was the one creating this presentation, I made it my favorite kind of presentation, which is the videos of robots doing cool things kind of presentation. So there's going to be a lot of that sort of material forthcoming. Okay. Big initial question is, what actually is MoveIt Pro? Where does it fit into my software stack? MoveIt Pro has two parts. Try to get the pointer working. Ooh, pretty cool. Yeah, okay, there we go. So the first part, there's a backend runtime part. So that's sort of the brains of everything. You know, this MoveIt Pro really heavily uses behavior trees, and we have a plugin-based system for adding behaviors or skills that the behavior tree can load. I'll talk more about that a little bit later. But there's basically a backend server that is managing the behavior tree, taking input from your operator interface or like a state machine that you have that's sort of controlling your workflow, and then it's generating the motion plans, doing the perception processing, sending requests out to other nodes in your environment that you may be adding for like ML segmentation or, you know, kind of other perception or processing related things, then sending the commands to the robot through ROS-I control or whatever control interface you have, and then making the robot actually move. The second part of this is on the left, which is there's a kind of like a developer platform user interface. So you can use that for monitoring the state of your robot, for tracking the progress through the behavior tree, for editing the behavior tree as well, for doing runtime configuration of the parameters in the behavior tree, all that good stuff. Worth emphasizing that the developer UI is useful, but it's not a required part of the system. You can be running this headless if you have some other way you want to control your robot. Here's a very long list of key features that we provide. There's a lot of different things that are related to like motion control. Some of them are pretty basic. You know, we have some tools for just moving between pre-programmed waypoints. We also have an interface for MoveIt Task Constructor, which is a task planner that you can use to find, you know, if you have a kind of a long motion or I guess a long plan of work, and there are many things that you have to do, like pick up objects and place them in a certain way. This lets you find a solution that is globally feasible. You know, you can find the right way to pick up the object that lets you place it into a constrained spot a little bit later on. There's interfaces with our Cartesian planners, so you can find singularity free paths, like rastering back and forth across different surfaces. And then there's visual servoing, which is like making your robot kind of track in real time some pose that you've determined by observing the environment, for example. For perception capabilities, there's a lot of stuff going on there. There's a lot of 3D point cloud processing for being able to sort of make sense of the environment, segment out objects that you want to interact with. We have an interface for machine learning pipelines. So that's actually handled as an action, a ROS action request. So, if you have your ML stack running as part of a separate node or on a completely different system that has a lot of GPUs in it because your ML framework needs, 32 gigabytes of compute, you can integrate that with your application running through MoveIt Pro. We have some tools for working with force feedback. You can use like exceeding a force threshold as an input to go into a different part of your behavior tree, for example. We have an admittance controller that lets you this is really fun. You can basically push around the robot based around the force that's measuring at its wrist. That's really useful for like following some toolpath across the surface while applying a certain amount of force, or doing like a peg insertion into a hole kind of problem. Then we've done a lot of work with grasping as well. The gripper interface is kind of agnostic to the actual modality of the gripper. So you can do two-finger gripping, you can do vacuum grasping, all sorts of things. And then a really important part of this that I want to emphasize is the infrastructure. The things that aren't necessarily part of like the happy path of the robot doing some operation. I mentioned that you can use the behavior trees to handle failure cases and fallbacks and errors. But there's also a lot of data logging happening in the back end. So you can, if something goes wrong, you can go back in the logs and figure out, this was the actual cause of that. You can do introspection of the task constructor solutions to see what the robot was thinking and why it made different decisions at each stage. All this is containerized as well. So it really makes it easy to deploy the latest version onto your system. You basically just pull it down and you have everything there and run it. And then we regularly patch this for security, maintenance, new features, keep it as reliable as possible. All right, so we get into the cool video part of this presentation. Oh, excellent. Okay, so this is the MoveIt Pro user interface. This is showing creating a new behavior tree to make this. I think this is doing something pretty simple, just moving the robot between different waypoints. So everything that the robot does in MoveIt Pro is a behavior tree. We call these building blocks behaviors, and you basically just drag them in and compose them in some order, hook them, and you connect them to each other by remapping the ports, which, if you're familiar with behavior trees, CPP, you connect to each other in the back end. And there's a very, very, very large number of behaviors that we've implemented from basically for all the categories that I talked about previously. I think this number is a little old. I think we're somewhat over 150 at this point. But in addition to these pre-built ones, we also have a C++ plugin-based API that you can use to create your own, load your own custom functionality into MoveIt Pro at runtime. Because this is all using the same interface, you can have your custom behaviors use the outputs of the built-in behaviors, and use the outputs of your custom behaviors as inputs to the built-in behaviors. So lots going on here. We put a lot of work into kind of solving robotics problems in a modular way with this. Let's see. Oh, okay. Yeah, this is about subtrees. One thing that I found is really important to making sort of a composable and modular application is having a way to, once you create like one small part of the system, like you have an objective to have the robot just like grab an object, right, and pick it up. You want to be able to reuse that later on. So this way you can drag in objectives and make them a component of other objectives. So this lets you have a really like modular and composable kind of application. All right. Yeah, and we tried to make as many parameters as we could tunable at runtime. So all of these behaviors have these sort of text inputs right now. These are controlling the parameters of what that behavior is actually doing. So you can run the objective, and then if you want it to be doing something different, you just go into the editor at runtime and you change the value of one of these numbers to make it, plan the raster paths in a different way, or change the acceleration limits of your robot. So this makes it really, really fast to prototype new things, because if you have a really tight loop of changing the objective of the robot, seeing it happen, making another change, and so on. All right, reference applications. So the reference applications are sort of pre-built robot configurations that we have that are doing some kind of high-level generic task. Well, some of them are really specific, but the idea is that you can use these as a starting point for your own application, and just do a little bit of customization or add your own custom behaviors to make it do something that's just a little bit different, but is solves your specific problem. Okay, so you start basic and then get more advanced. This is an example of doing Cartesian control, which is just following a set of waypoints that we've loaded in to make the robot draw our logo. These waypoints were generated with an offline tool and then loaded in as a YAML file. So you can picture, connecting that really easily to any kind of offline toolpath generation that you have. And this is, you'll see a few robots through this. This is a Canova 7-axis arm. So, we're able to avoid singularities and make use of that additional degree of freedom that we have for the 7th axis on the robot. So this is a little bit similar. This is sort of showing using the same underlying behaviors to do laser cutting. So the robot is localized to this, I think that's a composite plate using an AR tag, and now it knows the pose of it relative to itself, and then it's performing a Cartesian path to do some sort of cutting operation relative to that. All right, this is showing, I mentioned peg and hole earlier. Kind of two steps going on here. So the robot has we've taught it the mesh of the item it's looking for in the environment. So it's the thing on the bottom with the hole in it. So it takes a point cloud scan of the scene, and then it aligns its CAD model of that object to what it's looking for. And then once it finds it, it executes some behaviors to move this peg into sort of a relative position above it, and then insert the peg into the hole while monitoring the force measurements at its wrist. This is using the admittance controller, which we developed as part of ROS-I control. And that's able to sort of give some compliance to each axis of the robot, so that if the alignment is a little bit off or there was some friction, it knows how to correct and sort of get the item inserted all the way. Okay, this is another surface scanning example. So system knows, this is, I think it's a Marmon ring actually, which is sort of a satellite docking clamp. So the robot knows what it's looking for. It takes a scan of the environment and then it has a tool path that was defined relative to the origin of the object. So once it finds the object, it aligns the tool path to it and then performs the motion. Oh, okay. Yeah, this is one of the most complex objectives that we had, just because of all the fallback logic. This is a robot doing unstructured bin picking. So there is a box of objects just sort of randomly all thrown together. In this example, they're all the same object, but they don't necessarily have to be. So the robot goes and looks at the box, finds, uses ML, so it's specifically the segment anything model from Meta, to identify each individual object in that big heap. Uses some behaviors that do point cloud and image processing to find flat spots in those objects, and then kind of combines the flat spots so it knows which parts are on the same items. And then it tries to plan vacuum grafts to suction each object and place it in the other bin. So the behavior tree for this, there's sort of I talked about the happy path earlier, right? So there's if everything goes right, it's actually very simple to do something like this. but you have to be able to handle like, oh, what if the object that I thought I was going to pick up isn't actually reachable, or what if I go to grasp it and I don't have good suction and I don't actually pick up the object. So a really important part of what the behavior trees give us here is the ability to detect those kinds of situations and then do some sort of fallback action in order to correct for it and make sure that we do ultimately pick up an object from one bin and place it into the other bin. Yeah, this is a visual servoing example. As you can see from the video in the bottom right, this is supposed to represent like two satellites in orbit. So that's why we have the really high contrast lighting there. So we have the UR holding the cube is representing like something like a satellite that we want to grasp or dock with, and the Canova arm is tracking an AR tag on the satellite, and then trying to keep up with it as best as we can. So yeah, you can see the behavior tree status updating in the right. It's sort of continuously getting an April tag pose and then updating the servoing command to make sure that it's doing the best job it can of tracking the satellite. Okay, this is a demo that we put together with Johnson Space Center. They have a robotics group that we work with. And this is simulating a robot handling an automated delivery to a lunar base, I believe. So, there's the door kind of the hatch for a pod that just landed, and there's a cargo transfer bag inside of it. And the robot is exchanging the new bag with kind of the old bag full of all the space station trash or whatever that that we want to get rid of. So it has to do a very long sequence of actions that have some uncertainty built into them in order to do that cargo transfer bag exchange. Yeah, so this is there's a lot going on here, basically. So as the robot is doing this, it has to localize the position of each bag, plan collision-free motion through a really confined space, and then as it interacts with the environment to open the doors and close the doors and move the bags around, it has to update the collision model. So MoveIt Pro gives us the tools that let us do this, essentially. I talked about admittance control a little bit earlier. We also have an interface for sort of fine-tuning the parameters of admittance control. So let's say that you want your robot to be compliant only along the z-axis and really rigid when it's rotating or translating around any other axis. So the user interface has a kind of an advanced widget that lets you graphically fine-tune those. You can see exactly what robot axis you're adjusting the admittance parameters around. So again, it's an easy way to get quick feedback on something that would be very tricky to conceptualize otherwise if you're just doing this using kind of conventional, like editing a text file kind of programming. Yeah, you can do similar things with planning constraints as well. So this is how you solve the glass upright kind of problem. You say, a robot, after you pick up this object, I only want you to be able to rotate around some axis by plus or minus 15 degrees so we don't spill our glass. So we have a tool that lets you edit the inputs into the planning behaviors to solve that problem. Yeah, I talked about our integration with MoveIt Task Constructor. Yeah, so this lets you do very complex kinds of operations where you actually are modifying the planning scene as like a step in between executing different trajectories. I think I talked about this enough a little bit earlier. But this is really powerful. And I think that the tools that we provide here make it a lot easier to use MoveIt Task Constructor than if you're just writing, the C++ code kind of raw. Yeah, we have a robot site configuration system that lets you, it builds off tools that are kind of common in open source ROS. Like you just provide a URDF and a couple of YAML files that define the inputs to kind of customize your robot. Yeah, so it makes it pretty straightforward to have robots from different manufacturers, different configurations and sizes and equipment all working together. Here are some of the robots that we have deployed with MoveIt Pro so far. In general, any robot that has a ROS-I driver or a ROS-I control plugin, you can use with MoveIt Pro. So kind of the takeaways here. Question is, why should we be using MoveIt Pro? Robotics takes a lot of time and effort to get right. And so with MoveIt Pro, you can focus on a part of the problem that is most important to you specifically, and you don't have to reinvent the wheel. From my experience, I think when people think about about robots and and automation. They're kind of focused on stuff like the open source movement, for example. With the motion planning, and sometimes you don't think about the more like the telling the robot what to plan and when side of things until later, and then you're playing catch up. So we've already solved all of that basically. Put a lot of work into getting it right. And because PickNik has done a lot of services work, we see a lot of these projects go through. Basically you'll be able to finish your work much faster, like a year faster, and for a lot less money than if you were doing it all from scratch. So, thank you very much. If you want to talk more, there's a QR code for you to scan. Does anyone have any questions?
Questions for Joe? Paul, are you able to see the chat? Okay. Hang tight, Joe, because I have a question.
You have a question,
right? So you mentioned if the driver exists, have you guys been willing to help people like get the driver up and going?
Oh yeah, absolutely. That's a very important part of the work that we do.
Right, because obviously I think you collaborated with ABB on a particular application, right? So again, like additional services as well, with the help of getting drivers up and running, right?
Absolutely.
Any other questions for Joe? Bharat?
Yeah, the question is it open sourced or license-based? It's sort of some of both. So builds extensively on the open source part of MoveIt. In order to run MoveIt Pro, that you do need a license for that. The API for kind of defining how you interact with it and how you write your own plugins, that is publicly defined. Well.
I noticed that it was like quite a lot of readings, activities there. So are you collaborating with any like a TV camera sensor or any kind of what kind of 3D sensors
okay.
can you use?
Okay, yeah, so the question was basically, are we collaborating with any 3D sensor manufacturers in order to do this? Yeah, we are. Well, we are. I think a lot of that interaction is within the open source community, though. I mean, I think the most common 3D sensor that you see used there is the RealSense camera. So we use the ROS-I driver for that pretty extensively. And in general, yeah, as kind of same story was with robot control. You can bring whatever set of cameras you want, as long as it publishes ROS-I point cloud messages or image messages or whatever format the behaviors in question need to ingest.
I think it's fair to say, similar to the manipulator question, if a vendor or an OEM of perception hardware, they could probably reach out to with help of.
Yeah, that, absolutely as well. Yeah. Yes.
So you have about 30 people.
Yep.
So how do you fund it if you're not charging, right? Trying to figure out what the commercial side of MoveIt Pro is.
Oh yeah, I mean, so we're funded by revenue from licensing MoveIt Pro, and then revenue from services work related to that.
So what is that?
Let's see, I think it's about. Okay, so I think this may have changed since I looked at it last. If you go to our website, the licensing information is all listed there. Yep.
Another question, Corey.
The singularity free cartesian planning, using just one type of model, or like motion model, or is it bring together multiple types of motion?
Can you repeat that?
Okay, yeah. So you're asking about the singularity-free Cartesian planning and the motion model that it uses. I think this is mostly related to, as far as how we solve that problem, to how the inverse kinematics solver works. Yeah, okay, so this overlaps a lot also with how I think open source MoveIt solves that problem. Yeah, so there's a variety of different IK solvers that you can pick. I think we just basically did a lot of experimentation, picked one that we found gave the best results.
Question. Anyone in chat silent, Paul? We're clear on the chat? Well, great. Oh, Omar, one more.
Work or partner with any vision that do, like, say, an unstructured container that case by case.
Oh, so yeah, question about if we partner with vision companies and bin picking companies. Yeah, we have done that kind of thing before. Yeah, I think it's sort of related to the previous question. I think most of our interaction is through open source software. So. Anyway, yeah. So if you want to talk more, I mean, like I said, I have one of the hardware demo slots later today, so you get a much more hands-on look at this. Look forward to talking to you then. Thank you.
So thank you.